and weren't doing quantum computing to make fast computers as much as understand computation and quantum mechanics. Now that quantum computing's grown into an industry in many ways, I think some of the same people are reverting back to the original questions about the nature of computation and quantum mechanics. So I think one of the biggest consequences of quantum computing won't be faster computers, it'll be understanding nature. If nature can compute, then computation is an interesting language to understand nature. So that is background. I'm pleased to present two inconclusive results in that direction. Looking at ways to connect physical systems and computation. This is much of the work I'm going to describe was done with and by my student Jason Taylor, and a lot of the Ultrafast work was done in collaboration with Phil Buxbaum and his student Adrian Florian. So my early involvement in what became NMR quantum computing wasn't aiming at creating a scalable industrial computing technology. The last talk beautifully presented a lot of the challenges down one route for that. This was, in a sense, cheating. It was looking at what's the easiest way to start doing quantum computations. And we were struck in retrospect that just how exquisite a molecule is as a system for quantum computing. The nuclei is levitated in a trap, in effect it screens. You can get a large number produced to the same specifications at low cost. They tumbling averages environmental interactions. It really is an exquisite system. Even now, at this level of maturity, there's quantum systems with coherence, and there's quantum systems with controllable nonlinearity, and there's very little intersection. These kinds of molecules still are about the best technologically. That won't be true for, I think, very much longer. But that was the real inspiration of this, is what are early ways to start manipulating quantum coherence. But it became clear very quickly that room temperature NMR had a terminal scaling limitation in a Boltzmann factor, that the density matrix, because of the rapid tumbling and averaging to a very good approximation in thermal equilibrium, becomes a tensor product of all of these individual molecule density matrices. And then if you write that down, there's a partition function normalization. And that's what kills you. That's what gives you this exponential fall off in signal strength, the size of spins in the room temperature limit. So if you plot that, what I'm showing here is this is temperature, this is magnetization, and those little numbers are the number of spins. And you can get a sense of a scale factor for where polarization hits a floor from just the spin noise limit, from the limit of the spin fluctuations. And so at room temperature, around 20 or so spins, you're bumping into the spin fluctuation limit, where the polarization equals spin fluctuation. So that's about as far as you could ever hope to go. And you couldn't get to technologically significant number of spins, which is maybe 40, 50 is where it starts to beat conventional computation, until you get to very low spin temperatures. So that led in a couple directions. One interesting kind of back action is along the way to trying to get superpolarization, we wanted to squeeze as much sensitivity out from the spins as we could. So we revisited the whole signal chain and started looking at the probes, the conventional coils that are used. And we wanted maximum sensitivity, maximum pill fraction, and we're looking at scaling to much smaller samples. And we stumbled across a really interesting way to make probes. Through a circuitous path, we started looking at, instead of inductors, slot antennas. So a slot antenna is the opposite of an antenna. It's a current perturbation that's the inverse of what you want to make. And what we found was, by making micro strip lines with a micro slot, viewed externally, it's a impedance match 50 ohm strip line. In the vicinity of the slot, the electric field can't really see it. The electric field going to the ground plane averages over it. But the magnetic field has to go around this discontinuity. So you get this tremendous magnetic field concentration. But just by geometrical factors, it's very homogeneous. So the signal externally comes from magnetic interactions in the vicinity of the slot. And so the student doing this without much effort compared to the careers that go into probe building was able to show roughly the most sensitive integrated planar readout of spins. This is nanomolar picoliter sample sensitivity. And in particular, what's also nice about the microslots is they're easily parallelizable to mass-produce arrays of them. And they also need fields over this tremendously small volume. So this has forked off and now looks very interesting for molecular biology. That for the holy grail in molecular biology of being able to run a gel directly to do structural biology instead of having to amplify the proteins, this looks very promising for ultra small sample NMR. So this could count as one back action of this has nothing to do with quantum. This was born from quantum computing. It has nothing to do with it anymore, but it's a nice direction in integrated small sample probe design.
Okay.
Yeah, we went off to the companies you know well that do probe building, and they were kind of shocked at how this was beating their superconducting probes with just one grad student, and without even some of the obvious things you do to do, like, for example, this doesn't even have the homogeneity matching layers. So it looks very promising, and it's getting commercialized. But that, for quantum, any kind of scaling in quantum computing, though, that's still a band-aid, because that's the room temperature limit. So I'm blowing up that graph. Again, this is temperature, spin polarization, number of qubits. A standard trick from the 50s is ENDO, which is electron nuclear double resonance, where you transfer the electron polarization to the nucleus. It's essentially C0 in the electron nuclear spin system. It's just not called that. But because of the gyromagnetic ratio of the electron, you get this big win. But that only gives you a 0.4 K effective spin temperature. In rare gas atoms, you can do optical pumping, where then you get near unity polarization and millikelvin spin temperatures, and that's where this gets very interesting. And so that led us to ask the question of, can you pump molecules? The molecules have this exquisite spin coherence with these controllable nonlinearities. In atoms, we can do optical pumping that's like falling off a log to do. In molecules, the problem is the spectra aren't spectrally resolved. The spectra aren't resolved in frequency, so you can't address in frequency due to the optical pumping. So you have to work in the time domain. So can you do time domain pumping of a molecule to give electron spin polarization that you can then use to induce nuclear spin polarization? That's the question we set out to ask. There had been some work, but not much, on asking about how ultrafast pumping relates to spin order. So there's been a ton of work on ultrafast pumping on gases, a ton of work on solids. Warren Warren's done a lot of this. Very little, though, on liquids, and anecdotal results on liquids. So there's now an industry of making shaped ultrafast pulses for a range of other things, like breaking bonds, driving reactions, probing molecular states. The idea is you have a laser that produces fast pulses. You disperse it, you put it through some kind of shaper, put it through the sample, make a statistic, and then put this all in a big machine learning loop. This is much too nonlinear and hard to understand, so you put it in a big machine learning loop and see if you can figure out how to shape the pulses to make extremal some property of interest. From our experiments, I'll explain more where they come from. These are the kinds of pulses you get. This is time in picoseconds, frequency. You often see chirps, or this is an example of double pulsing. In any one experiment, the machine learning search might go through thousands of pulse sequences trying to make extremal statistic like this. So the first thing we did is a too ambitious experiment of connecting a pulse shaper to a cryostat, reading out a nuclear spin signal, and seeing if you can make it extremal. And the results of that were ambiguous. There was maybe some effect, didn't jump out. And so pretty quickly it became clear we were trying to make too many steps at once, to go from polarizing the electron to the nucleus, polarizing the electrons, get from the electron to the nucleus, read out from the nucleus. So we stepped back just to focus on the electronic spin system. And can we simply maximize spin order in the molecule? so this is what the spectra look like. In a second I'll talk about the molecules. But we were using molecules that had an inter-system crossing to a long-lived triplet state. And then if you look in the spectroscopy, there'd be singlet absorption and triplet absorption. And so just a simple figure of merit would be to come out here and sit on the triplet absorption and see if we could significantly modify the population through the inter-system crossing and park it out on the triplet part of the absorption spectrum. So we were using tetraporphyrins, ZNTPP, CUTPP, oligothiophenes, cardothiophines. These were all picked by having good absorption where the laser was happy at 400 nanometers, and then having long-lived triplet states to maximize what we were doing. And this is the sort of thing we would see, which is fairly generic for ultrafast lasers with almost anything. So this is plotting the relative population on the triplet line versus machine learning cycles. And there's about a factor of 2 improvement in that. So the machine learning can maybe make a 2x improvement in the relative population. That's not, there are a lot of things you can try to ask ultrafast pulse shapers to learn to do, and you get maybe factors of 2 wins. It wasn't a dramatic effect. What was a little bit suggestive, though, was that the states found to minimize and maximize the triplet population were chirps, and chirps with different slopes. We hadn't built the chirp in any way to the system. This was the pulse search went through all the kinds of pulses, like multiple pulsing, stuff like that. And it ended up pretty stably always finding chirps, but chirps with different slopes to minimize or maximize the triplet production. So the chirp seemed to be somehow coupled with creating the electron spin order. So we then just wrote a program to run the AO pulse shaper to simply step a chirp, to generate a chirp and sweep the chirp angle and look at how chirp related to triplet production. And this is what we got from that. The red is the pump power, because the pump power itself depends on the chirp. And then the blue is the triplet absorption. And so suggestively, there's a difference between the triplet absorption and the pump power, so that at slightly positive chirp, we are generating more angular momentum in the triplet state. So it did seem like we're enhancing spin order, but it's not orders of magnitude. It's not a big effect. There's some difference from the pump power, but it didn't jump out. This was a small enough effect also that we were a little bit suspicious, and so we did a sanity check, which is just simply to not shape the pulse at all, but simply hit the molecule with circularly polarized light, and ask if we were doing anything more sophisticated than shoveling in angular momentum. So this sanity check experiment was to go through putting in unpolarized light, left circularly polarized light, unpolarized light, right circularly polarized light, and what I'm plotting is the same statistic of a Faraday rotation of a probe. And what we found is if you just hit the molecule with circularly polarized light, we were getting about the same kind of triplet enhancement, which said that, in fact, the pulse shaping wasn't doing anything significant. It was just throwing angular momentum at the molecule that was finding its way into the triplet shape. But the pulse shaping wasn't really learning anything interesting about how to drive the inter-system crossing. So all of that left us with a conclusion that this wasn't like falling off a log. There wasn't a big effect in electron spin enhancement. There seemed to be a dependence on chirps, which is interesting to understand the molecular spectroscopy, but again, didn't seem to have a big effect. So there wasn't a quick win in ultrafast pulse shaping to get superpolarization, to use NMR-like techniques, but analogous to rare gas atoms in a high polarization limit. So that's the first inconclusive result. But there was an interesting moment that led to a very wide detour. We were looking at this data, trying to figure out what we might be missing to enhance spin order still further. And we were just tuning up the KLM. And for those of you who haven't seen Kerr lens lasers, they're a really interesting way to make fast laser pulses. I'll explain it in much more detail. And we're going through the slightly quirky process of turning it on, where you get everything set up, and then you tweak the laser to give it a little kick to put in some energy, and then it starts its ultrafast ringing. And Phil Buxbaum just made this passing comment that anybody who's worked with lasers like this makes, which is, it's sort of like magic. The laser finds the shortest pulse. It minimizes loss or maximizes gain. And while we were so busy trying to make all the system program molecules to compute without doing much enhancement, this laser was busy solving a very interesting problem. And it led us to start to think a little bit more about what's going on in the KLM itself as it rings up. So in a KLM, there's a pump laser, there's a laser cavity, there's this Ti sapphire crystal. This is dispersion and compensation. There's an output coupler. Conceptually, then, there's this aperture. In practice, the aperture is just the beam overlap between the KLM laser and the pump laser, but there's an aperture. And then the idea is that because of self-focusing, there's gain in the Ti sapphire. But self-focusing means if the energy increases in the pulse, it gets focused, and more of the light gets through the aperture. So the laser wins not by having the energy bunched uniformly in time, but by packing it in short pulses. And the tighter it packs the energy in the pulse, the more self-focusing you get. The more self-focusing you get, the more light goes through the aperture, and then the more gain you get. And so the laser minimizes loss or maximizes gain by finding short pulses. There's nothing in here that builds in short pulses. The short pulses are a solution to getting the self-focusing turned on. So when it's running, you get this mode locking of the modes in the cavity. Ultimately, there's a soliton shape that comes from a competition between self-phase modulation and group velocity dispersion, ultimately give you the shape of these ultra-fast pulses. And so it raises the question of what can you say about the ring up of a KLM laser? What is the problem it's solving? And is that an interesting problem, and what can you do with it? So now that was very suggestive of something wholly unrelated I had done earlier. So what I want to do now is go on a detour and talk about something unrelated, then come back and connect it to ultrafast lasers in a way that will almost but not quite connect as the second inconclusive result. So years ago, I was looking at nonlinear oscillators that could do spread spectrum generation. So in communication, a very important primitive is linear feedback shift registers that make maximal length coding sequences. And a lot of cycles in signal processors are spent on spread spectrum acquisition. That when you turn on a spread spectrum system, it's got to recover where you are in the chip sequence. And the standard solution isn't much fancier than you spin a correlator and you look for a hit. And I was struck by how nonlinear oscillators entrain. Nonlinear dynamics is a bad source of structured noise. What makes the dynamics interesting is that it has structure. But could you have the ideal structure of a maximal length pseudorandom sequence, but still have nonlinear entrainment? And so what I designed was some oscillators that did that. So these simple maps, this is a sending spread spectrum system. This is a receiver. If I perturb it, this map is doing the spread spectrum acquisition and tracking, the coding problem, but it's simply doing it by entrainment. So that was a number of years ago. More recently, we came to understand that that wasn't a one-off hack, but it was actually a special case of a graphical network. And then where I'm going is I'll show how graphical networks relate to physical dynamics. So graphical networks is an idea that's been invented many times over. In inference, it's called Bayes nets. In coding, they're panographs. There are many different names for it. The class of problems isn't arbitrary, but it is NP-complete. It's easiest described in the context of a semi-ring, which means a set of operators, like summing over products or doing a max over a sum. These sums and products comes up often in inference. You have a set of probabilities. You have multiplication for joint occurrences, and then you have sums for when you want to marginalize over every variable but one to make a prediction. And max sum comes from when you're doing log likelihood decoding. The sums is over the log likelihoods, and then the max is to find code words. And if there's no structure in the problem, these are classic NP-complete problems. All you can do is exponentially sum over everything. But if there is structure in the problem, you can use that structure to generate a graph of constraints, and then use the graph to generate an algorithm on the graph that solves the problem. And then what's nice about that is the graph itself naturally has a distributed implementation. So the easiest way to see how that works, and again, this is a detour that's going to end up back with how everything I described here abstractly relates to physical dynamics. So let's say we're doing an inference problem. We want to recover code words. Let's take the spread spectrum example. So these would be bits or states of the system, the circles. The squares are functional constraints. What does our code say about how the variables are related? And so if we want to find this bit, its probability distribution, we have to marginalize over every variable in the problem. However, because of the sparsity, that not everything is connected, we can first take the global density and decompose it into a product of densities of the groups of variables connected to the one we're targeting. We can then take this marginalization within those products and marginalize only over within these groups of variables. Then we can recurse by pushing that across the function into those variables, and then we can travel down through those functions. And you can build a tree where you do these recursions. And summarizing that, what it looks like is if these are variables and those are functions, a message passing algorithm looks like the following. Messages are functions you pass on these links in a graph. Variables send to functions a message which takes all their incoming function messages and locally weights them and sends them to the function. Functions take in their variable messages, multiply them, weight them by the function, and do the local marginalization. So these are each local operations you do on the links of the graph. If you have a tree in linear time, this gives you, the local operations give you an exact solution to the global problem. If you don't have a tree, if you have loops, then there's a longer discussion about, this is an approximate algorithm, and there's generalizations that give principled approximations to intractable problems on loopy graphs. So as an example of this that's closely related to physical dynamics, let's go back to that coding example. You have a hidden state that you're trying to recover. It has an update rule for its evolution. There's a density function for your observable, and then there's the observed distribution. So we want to go from these observations to these hidden states. If you just project down this density, that's maximum likelihood decoding. If you bring forward this density, the message passing tells you to multiply those, and that is in fact map estimation. And then in fact what's nice about this message passing language is if you've ever studied estimation, you're taught this and then you do some pages of math on Kalman filters, but there are a bunch of results that come quickly here. The most recent state estimate, the message passing only depends on the past history, and there's no loops here, so there's no approximation. So you can see right away the optimality of recursive estimation. And there are a number of nice properties like that you can show. And finally, if you look at this little block, it recurs. So rather than traveling through the trellis, you can roll up the trellis and let the data travel through it. And so finally what you get for this hidden state estimation problem is feedback to a mixer. So any engineer who makes anything does feedback to mixers, but you can see feedback to a mixer emerging here not as an assumed circuit element, but as something you derive from the underlying estimation problem. It's not yet a circuit. It's beginning to look like one. But this came from compiling, in effect, an estimation problem into dynamics that solves it. So for example, you can recover right away. If you want to recover phase of a carrier, even if you never heard of a phase lock loop, the signal generator is, say, a relaxation oscillator. You get bits. Here, a bit is, the state space now is P of 0, P of 1. We're in the state space of the digital system, which is a hypercube. But this is a probabilistic representation, so we can go into the interior. And then because probabilities are normalized, this is a single degree of freedom. So we're passing an analog degree of freedom that represents a probability. And then the inverters here become 2x2 matrices that operate on this probability representation. And then the feedback to a mixer multiplies these density estimates. So you derive a phase lock loop this way, but in an interesting way, you view the voltages in a phase lock loop as probabilities in the state space of a digital system, as the real understanding for what it's doing. And what that led to then was I had a few students work on revisiting that thing I showed you. I won't do this in detail, but this is an interesting kind of CMOS circuit. It's a soft gate. It looks a bit like an analog multiplier, but what it does is it takes these voltages that aren't bits, they're bit probabilities. It takes the voltages in the circuit and it does the soft logic, this probabilistic combination. And so if you make circuits out of these soft logic elements, you can make devices that do these coding problems. And they do them in a really interesting way. Instead of the usual division of labor, where you have an A to D, you have a low noise amplifier, then an A to D, then a DSP, the front end oscillator in effect does the coding. And that has all sorts of wins. You win in speed because you're not clocking the DSP, you propagate through the device. You win in power because you're not, once again, clocking the DSP. Interestingly, you win in performance because digital logic, bit slices at the beginning. You parse bits and then you code on them. Here you're in the state space of the digital system, so you bit slice at the end. You get driven to the corners of the hypercube, and you bit slice only on the final results. And finally, what I like about this is this didn't come from wishing for a multi-valued analog kind of logic. This really was a kind of a principled derivation. It starts from the problem statement, turns it into a trellis, does message passing on the trellis, and maps the messages into physical degrees of freedom. So in the end, this is volts, but it's a circuit that's neither a conventional analog circuit nor a digital circuit. This is becoming called analog logic, a kind of circuit that sits right between analog and digital. So message passing generalized that hack I showed you into how that was solving the problem. Now to relate it back to physical dynamics and hints at relating it to lasers, there's a really nice way to reformulate what I just showed you from Jonathan Yedidia. So we're making, in the problems I've discussed, extremal at density. We want to decipher a code, do an inference, solve a problem. Formally, I can write the density in an exponential family. So I've written something that looks like a partition function, but the denominator is just normalization, and the numerator is simply transforming a density into an exponential family. In that representation, Helmholtz free energy is a log of partition function. If we have a belief for the solution to the problem we're trying to attack, then the Gibbs free energy is U minus H. So you get sum of the beliefs times the energy minus belief log belief. If you then substitute in the partition function and do the sums, what you get is the Gibbs free energy is the log of the partition function that doesn't depend on the belief, and then this, which is the Kullback-Leibler distance, standard measure of distance between functions. So minimizing the Gibbs free energy corresponds to the density that is closest to the solution to the problem. Now, that's a very old problem, and it goes all the way back to, well, even before, but most recently goes back to Hans Bethe, did one of the earliest useful solutions. Because this is a standard problem in StatMech. And so the Bethe solution is, we can't solve this problem globally. This is a classic intractable NP-complete problem. But a simple thing we can ask for is consistency of local marginals. So we want to satisfy normalization. And the one other thing we want to ask is that the local marginals in our density be consistent, is one of the most rudimentary things we could ask for as a property of a solution. What that means is we're going to minimize the Gibbs free energy, energy minus entropy, and then we're going to do this as a constrained optimization. And so in doing this constrained optimization, we introduce two Lagrange multipliers. One Lagrange multiplier is on this term, which comes from this term, which is the normalization. And then this is the term where we're enforcing consistency of the marginals. So that's Bethe's approximation. And then we do a variational calculation to minimize the Gibbs free energy consistent with these constraints. And when you do that, a beautiful thing falls out. What you get is these Lagrange multipliers are exactly the messages I derived for you from that recursion. So in StatMech, you're familiar with, you have microscopic dynamics, you have maximum entropy. Lagrange multipliers appear with constraints like average energy, and they become the observables. Sort of by analogy here, what we're making extremal is the problem we're trying to solve. The Lagrange multipliers appear because of the locality of the graph underlying the problem. And they become the messages. The Lagrange multipliers are the messages carrying the solution to the problem. So that mapping, in fact, is an old one. Economists 100 years ago explained prices as Lagrange multipliers in a distributed computation done in maximizing utility. And in constrained optimization, what are called primal dual methods are full of, you pass Lagrange multipliers around to solve problems. But, so what this shows is, in that circuit that was ringing up on a code, you can understand it through, as a message passing algorithm, but more deeply, you can understand the physical interactions as Lagrange multipliers solving an extremal a constrained optimization for the dynamics of the system. In thermodynamics, we're given the constrained optimization by Maxwell and Boltzmann, but in these engineered systems, we can decide what we want to make extremal, and then the Lagrange multipliers carry it. So what this is beginning to lead to is a wide variety of systems. One example is analog circuits. Another is mobile code and distributed networks. One of the most interesting ones is computer networks themselves, where physical interactions become viewed as Lagrange multipliers in a distributed optimization. For example, in computer networking, which nominally has nothing to do with physics, there's lots of network protocols, but there's been beautiful results recently showing that you can write Lagrangians for a network, do this calculation, and then the Lagrange multipliers you derive recover familiar network protocols. And in fact, people fight over trade-offs in the protocols, and many of the fights turn out to be just a polynomial, and you turn an exponent, and you get families of protocols that people have been fighting about for years. And so this starts to be a kind of a statistical mechanics of engineering. A way to, in StatMech, it's sort of descriptive. You start from the dynamics and get a partition function that lets you describe the dynamics. This is StatMech run backwards. You write a variational principle, and the Lagrange multipliers get carried by physical degrees of freedom that then solve a problem. So all of this was the detour triggered by Phil's comment that the laser minimizes loss. That in other areas I've been working on representing Lagrange multipliers in distributed optimizations in physical dynamics as a way to code problems natively in how systems evolve. And so that led to the question of, could you do this in an ultrafast laser? Could you view the radiation field as one more kind of Lagrange multiplier and view this kind of variational formulation as a representation of what the laser is doing? So to look at what goes on in a KLM, there's a standard model from Hermann House's. There's linear loss and phase shift. There's saturable gain, this group velocity term, the amplitude phase modulation. And so all of that becomes House's master equation. This is a round trip through the cavity. You get this gain minus loss term. This is the group velocity dispersion term. This is the self-phase modulation. This is the self-focusing. And this master equation is a good model of KLM ring-up. It has the structure of a complex Ginsburg-Landau equation. In particular, then the gain has gain depletion, that there's saturable gain. This has a CW solution, and then it has a soliton solution, which is exactly the one I showed you before. People have looked for a while to try to find Lyapunov functions for that. There are good ones for stationary solutions. There isn't an arbitrary one known for that. You can simplify the equation near the equilibrium. Everything cancels, and the dynamics is really governed by these two terms that give you the soliton competition in the pulse shape. And for those two terms have the structure of a nonlinear Schrodinger equation. That has this Lyapunov function that suggestively looks a bit like an action. There's a square of the amplitude and a square of a velocity-like term. And so one question was just, if you take the nonlinear Schrodinger equation, conserved quantity, what does that do in the ring-up of a KLM? So this is modeling. This is frequency, amplitude versus time in the ring-up of the KLM, integrating that master equation. And if you look at, in quotes, that Lyapunov function from the nonlinear Schrodinger equation, it's not quite monotonic, but it's nearly monotonic. It's nearly a conserved property that's being made extremal. And so that started to look suggestively like these other systems where we're designing analog logic circuits to make properties extremal. And again, the reason to ask these kinds of questions are not to solve arbitrary computational problems in these physical dynamics. It's to solve problems that are relevant for what the systems do using their degrees of freedom. Like the example was coding recovery. Things that are not, right now, for example, in optical computing, you take the photons and you implement conventional logic gates using nonlinear optical elements. This is asking, are there more natural representations for optical information processing using these dynamics? So the first thing we looked at was, here's a KLM, but what we did was we took the output mirror. Before that was an aperture, and so you had the KLM ring up, because to get gain, the laser had to learn to squeeze the light together in time to get the self-focusing to go through the aperture. So the first thing we looked at is, what if you replace the output mirror with a mirror that now has this coding structure, like we did for the analog logic circuit, where you have delays, and the delays are chosen like you do for a maximal length spread spectrum sequence, to have a GF2 polynomial. So the idea is you only get gain from the mirror if the pulses have this LFSR sequence. And you could do that either by using phase as a representation, or with a combining beam splitter, using gain in the KLM medium. And the question is, could the laser find the maximal length sequence by having a mirror that only reflects on a code rather than a periodic signal? And sadly, what we found was that seemed like a neat idea, but the laser was able to cheat. That it, rather than the representation we had chosen, where it would hop phase and frequency, it was able to just pull the pulse shape to find a strictly periodic pulse shape that was pulled off from the KLM pulse, but that made the gain extremal. So it used a degree of freedom other than the one we thought we had given a degree of freedom to hop in phase. The laser rang up in a different way, but it sort of cheated, and it found a way to ring up that maximized the gain, but with a simply periodic sequence. It just found a slightly different place to make its pulses. So the lesson from that, in retrospect, was that there's a lot of phase inertia in this system. The phase coherence length is huge compared to the pulse spacing. This is a very hard degree of freedom to pull. So if there's any hope of something like this working, what we want to do is choose a representation that's a little bit more natural for the basis of the laser works in. So right now what we're doing is we're looking at a few representations. One is there's already this group velocity dispersion compensation in a KLM. In that part of the laser, we have this dispersion. And so that's a convenient place to put in a spatial mask where you map color to time. And so what we want to do is use a representation involving double pulsing, because we already are dispersing through that part of the laser. And then in particular, most recently, what we're looking at is putting molecules and electrically optical material, active materials in part of the feedback network, so that rather than a static structure, they can be used in selecting the representation. And so this is very preliminary work. These experiments are ongoing. But it's an interesting endpoint for me in the spirit of the meeting. So the second transitional emerging result is simple ring up of a KLM as a noise lock loop doesn't work, but suggestively these structures look a lot like these other physical systems we now understand that you can really describe their computation as a constrained optimization passing Lagrange multipliers. And this last place it's led us to is we had initially started with computers to control lasers to control molecules, and we finally are using the molecules to control the lasers, running the control loop backwards. And so in a very interesting way, it is a kind of a back action of we're using the physics to do the computation rather than using the computers to control the physics. And that long detour through the math that might or might not have made sense, I hope you can take away the spirit that there's computer programs which are descend from Turing and beyond as a model of computation. One of the biggest applications of computing are mathematical programs, which is constrained optimization. When I first learned about mathematical programs, I kept asking what that has to do with computer programs and was told nothing. Constrained optimization is just routing airplanes and things like that. But what's emerging from this work is that mathematical programs aren't just an application of concept, it's really a programming model. Constrained optimization with sparsity giving distributed solutions where you pass Lagrange multipliers, it is a programming model. It's a model of computation. It's NP complete. You can represent in that anything you can do with a Turing type model. It's a different model of computation. And in many ways, it's a model of computation that's much more fundamentally related how physical systems work, because steps in the computation become Lagrange multipliers that become physical interactions. So along with this evolution leading us to revisit the role of molecules in computation and lasers, it's pushing along, still inconclusive, but pushing along the development of mathematical programming as a programming model to think about physical dynamics. That using these gorgeous, exquisite physical systems we're developing to emulate Turing machines is a historically received solution that may not make a lot of sense, we're beginning to see a hint of a much more fundamentally physically inspired way to think about how physical systems compute. So with that, there's links off of this website and stories related to all of this in these books, and if there's time and interest, I'll be happy to take questions. Thank you.